This is section 5.4 on calculus, day number 2, and we are looking at example 5 here. It says oil is leaking from a storage tank at this rate. Part A, I have the curve graphed very roughly here. I could find more points, but I know it's doing something like this. Part B says, what is the value of R1 and what does it represent? So first of all, I plug 1 into the equation. We get R1 is equal to 99 and 11/12, or we could find the decimal approximation for that one. And the label would be in gallons per day. And what does it represent? It would represent that at the end of the first day, oil is leaking from the tank at a rate of 99 and 11/12 gallons per day. Question C says, how much oil has leaked out by the end of the 5th day? So I'll come over to the graph, draw in that vertical line, and I want to figure out how much oil is in this region. Now, if I look at my graphs, vertical axis is R of T, and that is in gallons per day. And the horizontal axis is time in days. So as I look, find what does the area of this region represent? It is days on the horizontal axis times the vertical axis, which is gallons per day. You multiply days times gallons per day, you get gallons. So that there is our value in there. And to find the area under this curve, the accumulated oil that is leaked out by the end of the 5th day, we are going to use the integral from 0 to 5 of R of T dt. Now, if we were to go to our calculator, enter in y of 1 equals this equation, and then do the integral of y1 from 0 to 5 dx, we would get a value of 496.528. Make sure you know how to use your calculator to do that. This integral isn't that difficult to do. We could integrate the negative t squared over 12. We could integrate the 100. That wouldn't be that bad. We could plug in the numbers. It wouldn't be horrible. But we have a calculator, so we'll use it, and it comes out to this value. Right now, I'm showing my work, but this really isn't answering the question. So I'm going to write something here. I would say that by the end of the 5th day, 496.528 gallons of oil have leaked from the storage tank. D is asking us how much oil has leaked out between the 5th and 10th day. So if I go back up to the graph, 5th day, 10th day, draw in those vertical lines. We are trying to figure out the area under that curve. That is the accumulated number of gallons between those days. So as far as the calculation goes, we're doing the integral from 5 to 10 of RT dt. And if I evaluate that in my calculator, it comes out to 475.694. So to answer this question then, I would say in the 5th and 10th day, 475.694 gallons of oil leaked. Follow-up in question D asked us, why is the answer in part D less than that, and it should say in part C? And what we're looking at here is, since the rate at which the oil is leaking is decreasing with time, the amount leaked out during this time period should be less. And also, as we look on the graph, the blue region is a bigger area than the red region. So from a couple of perspectives, it should be something less during this time frame. Question E says, what is the average daily loss of oil that is leaked out over these 10 days? So what we could do is evaluate the integral from 0 to 1 to figure out how much oil leaked out on the first day, the integral from 1 to 2, the integral from 2 to 3, figure out how much leaked out on each individual day. But even that makes it a bit static, so we don't want to go about it that way. Instead, if we could figure out how much total oil leaked out during those 20 days, and divide it by the 20 days, that would tell us on average how much leaked out per day. We call this the average value theorem for integrals. It is the integral from 0 to 20, r of t dt, and it's 1 over 20 minus 0. It's our upper bound minus our lower bound. And you don't even have to put the 20 minus 0 because that's just going to be 20 there. Go back to your calculator and evaluate all that. And what this should come out to is 88.889 gallons. So as I looked at the very first one, question B says, what is R of 1? That was 99 and 11/12. By the time we get to the 20th day, the amount of oil that's leaking out on any given day is substantially less. So the average daily loss of oil is 88.889. The last question, which is question F, says, what does capital R prime of t represent? Well, if R of t is already the rate of change, and we're taking the derivative of that, that is a rate of change. In other words, it is the rate at which the rate of change is changing per day. And it would be measured in gallons per day per day. We're going to talk more about the second fundamental theorem of calculus. I'm going to skip over this page. One thing it mentions at the bottom is the accumulation function. We're going to use the phrase accumulated change and displacement kind of in a similar fashion. Turn the page one more time. And now we're looking at the second fundamental theorem of calculus. Really, what is it saying? And it says f of x is continuous, then the derivative of an integral is essentially the function. We know that adding and subtracting are inverse operations. Square and square root are inverse operations. We also know that about derivatives and integrals. So as long as our function is continuous here, the derivative of an integral is the original function. Thing to note is that the integral is a function of t dt. It's something different than x. The lower bound is some constant, and we'll talk about why that's significant here in a second. But then once we take this integral, then we're taking the derivative with respect to x. Again, it's basically saying that the integral and derivatives are inverse operations of each other. There's a few special cases. This can be confusing or it can be kind of simple for us. And let's look at what this means. First of all, with this example 7. We want to find the derivative of that integral. So we'll copy this down. D dx of. Now if we integrate t squared with respect to t, that would be cubed over 3. Integrate 1 with respect to t, that would be plus t. And it's going from 0 to x. The fact that that lower bound is a constant is very significant, because now we know that with these definite integrals, the way that we evaluate them is to take the upper bound minus the lower bound. Carry down that d dx again. We would have x cubed over 3 plus x minus, now we plug 0 in, that's 0 cubed over 3 plus 0. And I made a show of actually putting the 0 in there, because once we found the integral, which we've done now, we've integrated, we've plugged in the upper bound and the lower bound. Now we're going to find the derivative of all this. So the derivative with respect to x, and that's why this x and this x being the same is significant. That's why this upper bound was x. Take the derivative of that, we get x squared. The derivative of x, and we get 1. Now here's a key point with this whole idea of a constant. Since this lower limit of integration was 0, well, the integral or the derivative of a constant is always going to be, even if this number was 50 or 1,000, the derivative of a constant number is always 0. So the derivative of all this is gone, and this then is our answer. No coincidence that it is essentially the same as our original function. The big difference is instead of t, we have x. And there'll be a few more variations on these that we look at in the next few days.